yesterday we talked about imaginary numbers. We talked about complex numbers, which are a combo of real and imaginary. You should have a little bit of space on yesterday's notes, like down at the bottom here. Do we all have a little spot that we could donate to something? To a cause? Someplace, somewhere. If you don't, you can write it somewhere else in a notebook or wherever you'd like to do it, on your homework even. I just want to talk quickly about how to graph in the complex plane. So graphing in the complex plane. So typically we graph in the Cartesian coordinate system, which is like looking at your x's and y's and looking over the set of reals. But there's also a complex plane that exists that you can graph in as well. When we think about the complex plane, it looks like a normal graph. This is your real axis, and then this is your imaginary axis. And I kind of had thought that maybe you had seen it before, but like I said, second hour, most people felt like no, they hadn't, so I just wanted to talk about this quickly. If you come across a complex number like 2 plus 3i, and you're asked to graph it, this matches to the ordered pair 2, 3. So you take your real, and then it's comma, the coefficient of your imaginary. So this, if you needed to graph, would correspond to this. Over 2, up 1, 2, 3. So I've got my ordered pair right here. So if I wanted to graph 2 plus 3i in the complex plane, that's where it would. Okay? What do you guys think? Have you seen this before? Some of you, yeah? Okay. Part of the reason I show you this too is because I'm a firm believer in something called spiraling, which is where you see stuff and then it comes back again later and it comes back again later. And so I feel like the more times you see something, the better. And we are going to see graphing in the complex plane again in chapter 8 when we get into some stuff called polar coordinates. And so I kind of like the idea of talking about it today and just making sure you see it and have one experience with it, so when we get to it later in chapter 8, it's not brand new. How do we feel about this, okay? Alright. Go ahead and flip. We're going to go to section 3.6 now. Complex zeros and the fundamental theorem of algebra. So we really have two things on the docket for today. And again, the notes take a little while to go through. Number one, because the first bit is a little bit tedious, and you'll see that in a second. Number two, because the second part, we have to kind of go through the solving process. So we are going to solve today, and everything is on the table. So at one point when we were solving in this journey, we were solving and we were only getting real, rational answers. And then irrationals came into the mix, and now complex answers are in the mix too. So any of these solutions are fair game and things that I can find and see as solutions. I'm going to talk to you about what the fundamental theorem of algebra says, and I'm sure I say it in a weird way that no one else explains it, but I'm going to kind of tell you my way that I process and understand it. And if you have questions, make sure you ask me. It's also in your book, and it's written a little bit more mathematically, we'll say. Alright, here's what the fundamental theorem of algebra says. It says, you come across a polynomial out in the wild, and your coefficients are all nice, real numbers, and they're also rational. Okay, so you come across a polynomial, it has rational, we should really say and real and rational. I don't know what order I like that in. It has real and rational coefficients. Do you agree that all my coefficients are rational in that pretend example, and they're all real? They're no lie. Okay, so if you come across a problem and it says solve, and when you go through the solving process, you start getting imaginary solutions or irrational solutions. They travel in what I call the buddy system. So if you get, for example, let's say you solve and you get root 5 as a solution, then I guarantee that negative root 5 is also a solution. Because think about multiplying it back out, they would cancel, and that's the only way you could get back to an equation like this. Right? Do you see how this one has no roots? So you need that buddy system. Same thing here. Do you see we've got the complex pairs or complex conjugate pairs there? Again, think about multiplying them back out. The only way to get back to an equation like this, if you have something imaginary, is for them to travel in the buddy system. So please know that when you're solving, any irrational answer and any imaginary answer should travel with a buddy. And the buddy is always their conjugate pair. So if you have positive root 5, it travels with negative root 5. If you have 3 plus 5i, it travels with 3 minus 5i. So to me, I call it the buddy system. You'll probably never hear anybody else call it that. That's just the way, like I said, it's the way my brain processes it, that those two have to travel together as buddies. Because if they don't, you wouldn't cancel out and get a nice polynomial. All right, are you ready? And that's kind of what this conjugate zero theorem says as well, is that they have to travel with a buddy. So if you have an imaginary solution, it has to travel with a buddy. So if 2i is a 0, then so is negative 2i. Remember, 0 is a word for solution, right? 0, root, x-intercept, solutions, they all mean the same thing. If 1 minus 3i is a 0, what else is? What's its buddy? 1 plus 3i. Okay. So the first thing we're going to do is actually work backwards. Okay, we're going to get into solving in a second. First thing we're going to start with is working backwards. We have a function q, and it has degree 3. Okay, so that's the first thing I know. It tells me that I have solutions of negative 2 and I. Very sad day. My favorite pencil's out of blood. It's okay. It's going to be fine. It's going to be great. Oh, there's another one! Oh, and it has what? All right, good news. Well, we are ready. All right, back in business. All right, so negative 2 can travel by itself. So again, rational solutions can travel alone. They don't need a buddy. They are self-assured. They can go by themselves out into the great world. I can't travel by itself, right? Who does it travel with? It needs a buddy. It's nervous. Negative I. Same thing with any group. Any irrational numbers, they also are going to travel with a buddy. So anytime you come across i's or irrational numbers, again, buddy system. Now, do I have enough zeros here to match the degree? Perfect. Now, we've got to think backwards and think where it came from. If negative 2 is a solution, it came from x plus 2. If I is a solution, it came from x minus I. So think about that for a second. Remember that this is the zero product property that we're using. And so what the zero product property says is if we have a bunch of things that multiply to give us 0, one thing along the way must have been 0. Think about subbing in I. Would I minus I give you 0? That's why that works. And then this one will be x plus I. So basically the game I'm playing is I'm changing the sign in front of the term. Now, we're going to FOIL it back out because we want to find the equation that it came from. I know that these two are the more problematic sets of parentheses, but we want to multiply them together first because stuff's going to cancel. So if you have two sets of parentheses that have i's or have roots, you always want to start there, even though that might not be your first inclination. X times x. Here's ix minus ix and minus I squared. What happens to my middle two terms? They cancel. I have x squared And then what is this? Plus 1. I love it. So it's plus 1 because I squared is negative 1, and negative 1 is really 1. Okay, now let's bring down this x plus 2 that I had my thumb over. And now let's multiply that. So again, we're working backwards, and instead of finding solutions, we're finding the equation that gave us these solutions. All right, x times x cubed. Here's a 1x. Here's a 2x squared. And here's a 2. Again, sometimes I'm picky, sometimes I'm not. I'm going to be picky here. Do you see how it's not in standard form? I'm going to switch it to standard form. I like decreasing order of exponents always, always. So this would be my final answer. So what polynomial gave me those solutions? This polynomial. And they told me to name it q, so I can even write it out. Q of x equals, it would be this polynomial. Okay? Next one, we have another degree of 3. So how many parentheses should I have? 3. So the first parenthesis is going to house 1 as a 0. How would I do that? X minus 1. Now, do you see how this is like a whole thing? Right? Like we've got this situation here. So I'm going to do bigger parentheses, and I like to go a parenthesis within a parenthesis. Somebody last hour said, can I do like brackets or other grouping symbols? You sure can. I just double up with parentheses personally, but you can use whatever. Do you see how we did x minus and then whatever the other term was? Like we're always doing x minus. So that's what's going to go out front here is x minus, x minus. And then in the parenthesis is going to go your solution. So 15 minus 6i and 15 plus 6i. Think about the fact that this is the zero product property and we want it to equal 0. Think about plugging this in. If I plug this in, 15 minus 15, 15's gone. Negative 6i minus negative 6i, so plus negative 6i. So those would be gone too. So it's, again, it's the whole zero product property idea that if I plug this in here in place of x, it would zero out, is the goal. Okay? And same thing here. If I plug this in, if I did 15 plus 6i minus 15 plus 6i, they're going to zero out. Okay? All right. I know that, again, your first inclination is probably not going to be like, hey, let's multiply those two. They look amazing, right? That's not your first inclination, I don't think. However, we do want to do that because if you get this one involved, it's going to make it worse. So the first thing I'm going to do is distribute my negative into the parentheses, and I'm going to look at these two polynomials right here. And again, I'm going to pretend like this one doesn't exist for a minute. So I get x minus 15 plus 6i, and then I get x minus 15 minus 6i. Alright, so now let's multiply that out. X times x, x squared. This is where things get a little tedious. X times negative 15. Negative 15x, right? And then this is going to give me negative 6ix. Alright, let's multiply through the negative 15. Negative 15x. Oh wait, negative 15 times negative 15. That's going to give me, sorry, I wasn't looking at what I was doing there. That's going to give me a positive 225, right? 15 times 15. Oh shoot, I jumped. Oh my god, I did jump ahead. Oh people, I'm so sorry. I did jump ahead. Okay, so 15 times x, that is going to give me a negative 15x. I'm sorry, I jumped ahead. This is what happens when we've got so many things to multiply. negative 15x. Now, negative 15 times negative 15. That gives me a positive 225. And then negative 15 times negative 6 is going to give me a positive 90i. How are we doing so far? Okay? Okay, let's distribute the 6i next. This gives me 6ix. This gives me negative 90i. This gives me negative 36i squared. Okay, what can cancel? Flash you. Yep, the 90s. What else? Yep, the 6ix's also go away. So I have x squared. There's nobody for that. There's no other like term to combine. Negative 15 minus 15 more gives me negative 30x. And then this is really 225 plus 36. So 225 plus 36 is going to give me 261. So again, remember this is really minus a negative, and that's how it turns into that positive value for us. Okay, now, what do I still need to do? I was covering this up. I've still got to multiply by that. Again, like I said, this is the tedious part. I'm going to distribute the x through first. Again, I kind of think of this like double distributing. I'm going to send the x through. X cubed minus 30x squared plus 261x. Now I'm going to send the negative 1 through. Negative x squared plus 30x minus 261. Do I have some like terms I can combine? Yes. Okay, so x cubed doesn't have any buddies, that's fine. Negative 30x squared and negative 1x squared. Negative 31x squared. 261x and 30x. 291x and then minus 261. Did the 6 first? Yeah. I did like, let me get that. Okay. And it wanted that to be p of x, so we can say p of x equals this whole function. How'd we do, okay? The only thing I want to mention is that sometimes they'll tell you you have a solution with a multiplicity. If they had told me I had a solution and it was 1 and it had a multiplicity of 2, I would need 2 sets of parentheses of x minus 1. Does that make sense? Okay. So just be careful with that. Alright, here we go. Now we're on to the solving part. How many zeros do I need to find for p of x? 4. I'm not going to make you do the possible rational zeros, so this isn't a thing that we're going to do. We're just going to go through the solving process, and again, I kind of think about that like troubleshooting sheet that I gave you guys as kind of my guide of how I'm going to solve. Alright, so I always try to factor first and foremost. Can I factor that math? Can I? Do you see like an easy way? I don't either. So I don't try to factor for long. Again, I've been factoring for many a year, and if I look at something and I'm like, yeah, that's not going to happen, usually I just move on with my day. Okay, go ahead and type in your equation. So the second step is, if you look at the equation and you're like, bummer, I can't factor and solve. And to me, factor and solving is usually the easiest way and the fastest way. So if you can't factor and solve, I switch to my calculator. So here's my equation, here it is, typed in. So type yours in as well and hit graph when you're done. Your once you get to the graphs. And that's that you're not going to see 4 solutions. Okay, so hit graph when you're ready. And you should have a graph that looks similar to mine. If your window is off, remember you can press Zoom 6 to get back to a standard viewing window. Alright, do you see how the 0 on the right, the one over here, looks like it's at a nice number? Let's go to our table and see if that's true. So I'm going to hit second graph. And do you see how my 0 is at 5? So that's one of my solutions. The other solution isn't there. Now, do you see how I can tell where it lives? Do you see how it went from negative 25 to a positive 30? We had to go past 0, right, for that to happen. So my solution lives in between 0 and negative 1, but the question is where? So I'm going to go back to my graph and see if it's at least a nice value. So I'm going to press second trace, and I'm going to find a 0. Left bound, so I'm going to arrow up and to the left. Do you agree the blinky cursor is up and to the left?
Yes.
Like barely, right? But it's there. Okay, down and to the right. So I'm going to go down here into the abyss. Down and to the right. And then it says yes, and that's about as close as I can get. Do we know that decimal? Yes. That is negative 1/2. Now, there are 2 missing. 2 solutions that are MIA. That could mean one of 2 things. It could mean that they're imaginary, and so they're not showing up on the real graph. It could mean that I have multiplicities within the 5 and the negative 1/2 somewhere. So we don't know what the situation is. So what we're going to do is we're going to pull synthetically the 5 and the negative 1/2 out. It doesn't matter which one you pull out first. Just that you make sure that you pull both of them out. So set up your synthetic division. I'm starting with 5. If you want to be a rebel and start with negative 1/2, be a rebel today. Okay, that'll be fine because we'll end up at the same exact spot. Remember, one thing to be careful of in this process is that as you're looking at the equation, if you were missing a term, right, like if I had been missing the x squared term, I would need a 0 there for a placeholder. Do you remember that? So that's something to be careful of. If you're missing a term, make sure you put in a 0 for a placeholder. Here we go. Remember, add, then multiply. 2 plus nothing is 2. Multiply. Add down. Multiply. Add down. Multiply. Add down. Multiply. Add down. Love it, because what were we hoping would happen? A 0, because then that tells us that truly was a solution. And that should happen again, right, with the negative 1/2. So I'm going to set up shop right underneath, so I don't even have to like rewrite anything out. I'm just going to set up right there. And I'm going to do synthetic division all over again. So I'm whittling away, I'm pulling out solutions. 2 plus nothing is 2. Half of 2 is 1, and then it's also negative, so that's going to be a negative 1. 3 minus 1, 2. Half of 2, 1, and again it's going to be negative because I'm multiplying by a negative. I get 10. Half of 10 is 5, and I multiply by a negative, so it's negative 5. So again, do you see how that worked out nicely for me? Like it was supposed to. What do I have left? This is my constant, this is my x, this is my x squared. I have 2x squared plus 2x plus 10 equals 0. Now, I can actually simplify this a little bit more. Do you see how everything over here is divisible by 2? I'm going to divide each side by 2 because that's going to make it even nicer. Somebody last hour said, ooh, what if I didn't see that and I just started doing a different solving method? you're still going to get the same answer. So if you don't notice the divide by 2, that's fine. We'll still end up at the same spot. This gives me x squared plus 1x plus 5 equals 0, because 0 divided by 2 is 0. I've got a nice trinomial. Do we know what multiplies to 5 but also adds or subtracts to 1? That's a bummer. So that means I need to use quadratic formula. A is 1, B is 1, C is 5. Opposite of B, plus minus, square root, B squared. 1 squared is just, well, it's just 1. Minus 4 times A times C all over 2 times A. 2 times 1 is just 2. So again, you can kind of simplify as much or as little in your head as you can as you're going through the steps. What happens under my root? What do I end up with? Negative. So I've got negative 1 plus minus the square root of negative 19, because this is 1 minus 20. 1 minus 20 is negative 19. Now, we're never going to leave negatives under the root. That's a no-no. What should I bring out front? An I. So negative 1 plus minus I root 19 over 2. Is there any more simplifying that can be done here? No. There are 2 solutions embedded in here. Agree? With the plus minus. And then I already had 2 solutions over there, the 5 and the negative 1/2. Have I found all 4 solutions? I sure have. So 1, 2, 3, 4. So we've got them all. Most of these aren't going to ask you for the fully factored form. So this is good enough that we have our list of solutions. And again, if you want to kind of summarize it and write out your list of solutions, 5, negative 1/2, negative 1 plus minus I root 19 over 2. So you could write it out so it's just one kind of set there. As long as I can tell, like if you go back and box in your solutions, as long as I can tell, you don't have to do this. But sometimes it's nice just to kind of sum it up and give that final one. Alright, I'm going to give you one more solving one. This one says something about zeros, but that's not what I'm going to do. So I want to steal my example from last hour. So we're going to solve again. So this is solving part 2. And I want to solve x to the 4th. Question or stretch? Go ahead.
Will you ever ask us for the factored form?
I'm not probably going to do that very often, especially not with these, especially not with something like this. But again, how would I do it? I set up x minus, and then I set up the inner set of parentheses, and I just put this in.
Okay.
So it's not terrible, it just doesn't look nice.
Yeah.
Okay, for the next one, I'm going to do another solve. Do you agree that's a trinomial? Look at your pattern. Do you see how it's a higher degree trinomial? So it's 4, then 2, then a constant. Okay, so let's try to factor it like a trinomial. It'll be x squared in the first spot, because x squared times x squared is needed to get that x to the 4th. Okay, play the game now. Are there 2 numbers that multiply to negative 36 that add or subtract to negative 5? 9 and 4. Which one gets a plus, which one gets a minus? Minus 9 plus 4. Okay. I'm not done factoring. Again, how do you know when you're done factoring? Everything should be to the first power. Are those first powers? Nope. Okay. This breaks into a difference of perfect squares. How does that factor? Huh? X plus 3x minus 3. Perfect. Now, did you know you could factor a sum of squares? Ooh, this is the I thing. Here we go. I'm going to show you. If you didn't know, you're about to know. Alright. So you factor it the same way as the difference of squares. One gets a plus, one gets a minus. What's the square root of x squared? What's the square root of 4? 2. Now, there's one issue if we leave it like this. So, do you see how the 2x's and the negative 2x will cancel? That's lovely. All nice. X times x, x squared. What's the problem? So, how do you factor a sum of squares? Just like a difference of squares, except they both get an I. Here's why. Ready? Now multiply it back out. X times x, x squared. Good news. 2ix minus 2ix. Do those cancel? Yup. Positive 2i times negative 2i is going to give me negative 4i squared. Negative 4i squared is 4. Alright, what's my solution here?
Work with it.
Negative 3, positive 3, negative 2i, positive 2i. And again, you can rewrite it kind of like a nice little summative statement at the end, like this. Now, we finished a little bit faster than last group. I'm still not going to have you start on